Alright, so welcome to the last lecture for Module 1, P3. So we'll be looking at radicals and rational exponents. Let me just kind of walk you through an intro of what this stuff means. So normally if you have the square root of some number like 64, it's asking a question. It is asking if you want to evaluate what is this thing. It's asking you for which for which number x does x squared actually equal to 64? So in this case that answer would be 8, since 8 times 8 equals 64. Okay, what about higher number radicals? What if we had like the cube root of 8? Well, this number, basically, this root number, tells how many, let me erase that, how many copies of the unknown value you're actually multiplying. So this would be saying how many copies of the unknown factor, in this case, equals 8. So that means for which x does x to the third power equal 8? So in this case we would know x has to be equal to 2, because 2 to the third power equals 8. 2 times 2 times 2 equals 8. So we might write, if they asked us to simplify the cube root of 8, that equals 2. And it's the same way with any other power. So if you were looking for, say, the fifth root of 16, we'd be asking for which x does x to the fifth power equal 16. And again, this would be 2, because 2 to the fifth power equals 16. So if you were asked to evaluate this number, you would just say it's equal to 2. So that little root notation tells you exactly what power of the factor you have to solve in the other equation to actually simplify it. So notice when you're taking the root of a number larger than 1, you're actually going to end up with something smaller. So let's just keep that in mind. Alright, let's go back to the learning guide and start with some of the examples there. Where did I put? I think over here somewhere. Sorry, still kind of learning my way around OneNote. Alright, so section P3, radicals and rational exponents. So at the end we'll actually see how to convert between the radical notation and the normal exponent notation. Alright, so the first one, evaluate the square root of 36. So here we would say the square root of 36 is equal to 6, and the reason is because 6 squared equals 36. So if you would want to call, basically we'd be asking for which x does x squared equal 36, and that's the number 6. Okay, evaluate negative 36. Well, order of operations, we do the square root. That acts like parentheses before we do the negative because it's outside. So this would be the same thing, but it would just be equal to negative 6. So basically do square root first, then the negative. So we'll see that when we're doing the square root of a negative number, that is undefined in terms of real numbers. But a negative on the outside of a square root is perfectly fine, and we just apply that second. Okay, square root of 1 over 81. So there's a couple ways to think about this, but it's basically the same sort of thing. So for what x does x squared equal 1 over 81? Well, we know that 81 is equal to 9 times 9, so that kind of gives us the obvious guess. But we would say x equals 1 over 9, since, remember, when we multiply fractions, 1 over 9 times 1 over 9, we just multiply straight across, and you'd have 1 on top and 9 squared on the bottom, which is equal to 1 over 81. So this square root of 1 over 81 is just actually equal to 1 over 9. That would be your answer. Okay, 1D, we want to do whatever, so anytime you have something underneath the whole square root symbol, we want to do that first. So do 25 minus 16 first. It behaves like it's in parentheses. Then apply the radical. So we have the square root of 25 minus 16, which is equal to the square root of 9, which equals 3, because 3 times 3 equals 9. Okay, so anytime you have things you can simplify underneath the square root symbol, it's always a good idea to do those first. Okay. Notice here, though, the 25 minus 16, differently than the previous example, is not all underneath the square root. So here we have to do the square root separately before we combine. So simplify. Before combining. So in this case, the square root of 25 is equal to 5, and the square root of 16 is equal to 4. So we just end up with 5 minus 4, which equals 1. Same here, so underneath the square root in number 2, we can actually do some simplification first. So the square root, squaring negative 13 actually makes that a positive number, so we'll be able to take the square root. So this is just going to equal the square root of negative 13 times negative 13, which is going to give us a positive value before we have to apply the root, so it's going to make sense. So this will equal the square root of positive 169, which is just actually equal to 13, because 13 times 13 equals 169. An interesting thing to note about any time you have the square root of a number squared, so if we end up ever with something like the square root of let's say some number x squared, this actually always ends up just being the absolute value of x. Because notice, when you're doing a negative number squared, you get the same as if you would do the positive number squared. So when you do the square root of a number squared, it's always just equivalent to doing the absolute value. So you could see that with some other examples. So example, gratia, the square root of 5 squared would be positive 5, but so would the square root of negative 5 squared. That would also be positive 5. So that's just a nice little point to note. Alright, simplify the square root of 50. So one of the things that we can do when we have square roots is we have a little rule. If you have the square root of a times b, this is the same as doing the square root of a times the square root of b. So we can simplify square roots by identifying numbers that we know are perfect squares and then writing them separately. So how would we do that here? Well, we know the square root of 50 is really the same thing as the square root of 25 times 2, then we can use that rule we just did to the left and write that as the square root of 25 times the square root of 2. And then we know the square root of 25 is really just equal to 5 because 5 times 5 equals 25. So we just end up with 5 square root 2, or 5 times the square root of 2. Okay. The next one, generally I like to, so we can put them together using the rule. So when you multiply 2x and 6x, you end up with the square root of 12x squared. And then I always like to separate my regular numbers and my variables just to make things simple. And basically, what can I do? Well, I can write 12 as 4 times 3 because 4 is a perfect square. And then I already know that the square root of x squared is just regular old x. So when I put this little end on my square root symbol, I'm just basically noting that's where the square root stops, and everything after it is just a regular number, not a part of the square root. So here we can split this up as the square root of 4 and the square root of 3, and we know the square root of 4 is just 2 because 2 times 2 equals 4. So we'll end up with 2 times the square root of 3 times x. And that would be our final answer. Okay, square root of 49 over 16. So similarly to the fact that the square root of AB is the square root of A times the square root of B, we also have that the square root of A over B is equal to the square root of A divided by the square root of B. And that will help us take care of this next problem. So we can write the square root of 49 over 16 as the square root of 49 over the square root of 16. So remember that 7 times 7 equals 49, and 4 times 4 equals 16. So this is just going to simplify to 7 over 4. And if you're not too quick with your just mental arithmetic, then remember on the Blackboard page we always have that calculator you can use to help you determine whether something is a perfect root or not. So let's go down to this next one and see about doing it. Okay, so here we actually have things as separate radicals. So if you notice in this example, for A, we took the big square root and divided it into two smaller ones. Well, actually in 4B, we're going to work the other way. So we can use this rule and go from right to left as well. So we want to take the square root of 48 over x cubed over the square root of 3x and make that a single square root, because then we can apply some of the exponent rules we learned in lecture P2. So this will end up as the square root of 48 x cubed over 3x. And then we saw in the last lecture series that we can just do the regular numbers, 48 over 3, and that will give us 16. And then x cubed over x, we can subtract the exponents. 3 minus 1 is 2. So really, that whole fraction vanishes, and we just have the square root of 16x squared. And notice we can split that up into the square root of 16 and also the square root of x squared, which are basic square roots that we know. The square root of 16 is equal to 4, because 4 times 4 equals 16. And the square root of x squared is just equal to x, because x times x is x squared. So that whole complicated expression we started with turns out to really just be 4x in disguise. Alright, again, number 5, this one looks like it's involving some stuff with square roots, but really, if you look at the square root 17x, you can't simplify that. 17 is a prime number, so you're not going to have anything simpler such that x times x equals 17, and x is just to the first power, so you're not going to have anything simpler to break that down in terms of. So really this is just like 6y minus 8y, or 6 apples minus 8 apples. It's going to leave you with negative 2 apples. So we just end up with negative 2 times the square root of 17x. So basically, remember we discussed like terms. Like terms are similar as long as everything that comes after the regular numbers looks identical. 6 is a regular number. Square root of 17x is complicated, but the square root of 17x comes after negative 8 too. So we can just add the regular numbers and keep the complicated part at the end. Okay, 5b, they don't look alike right now, but maybe when we simplify the square roots we can make those end up looking similarly. So 18 we can write as the square root of 9 times 2, and 50 we can write as the square root of 25 times 2. And then we know the square root of 9, and we know the square root of 25. The square root of 9 is equal to 3. The square root of 25 is equal to 5. So we have 3, and then the square root of 9 turns into another 3, and then we're left over with 1 square root of 2. Then we have 5. Square root of 25 turns into another copy of 5, and then we have a square root of 2. Now multiply your regular numbers, so we'll have 9 square root 2 plus 25 square root 2. Okay, so now we are left with two terms that are alike. So we started out with ones that didn't look alike at all, but now they are. Square root of 2 comes after 9. Square root of 2 comes after 25. So just add up your regular numbers. 9 plus 25 is equal to 34. So we have 34 copies of the square root of 2. Or 34 times the square root of 2, excuse me, not 34 copies. If I said 34 copies, that would have meant square root of 2 to the 34th power. So just 34 times the square root of 2. Okay, so now we're going to talk about rationalizing the denominator. And when they say rationalize the denominator, they just mean we don't want to see any square roots in the bottom. So the way you go about doing this is you just use the fact that if you have the square root of 5 times the square root of 5, that is equal to the square root of 5 squared, which equals positive 5. Whenever you have a square root and you multiply it by another square root of the same value, you just get the regular number back. So here, we want to rationalize the denominator. But the problem is, it's an expression, not an equation. So we cannot just multiply willy-nilly by whatever we want. So if you have something that's an expression, the only thing you can do is multiply by something equal to 1. So we know that if we multiply by the square root of 5 on the bottom, that will get rid of that radical. So to multiply by something equal to 1, we just multiply by the fraction that is equal to 1. So square root of 5 divided by square root of 5 equals 1. So by multiplying by this fancy looking fraction, we're really not changing our expression. We're just changing it around a little bit. So on top you'll have square root of 2 times square root of 5. And on the bottom we'll have square root of 5 times square root of 5, which over here we saw was equal to regular 5. So this is just equal to 5. And then using that first rule we've been using so much, we can just multiply these two together to get one square root. So we end up with a square root of 10 over 5 as our rationalized fraction. Here's a cool one. So whenever you have something that looks like square root of a plus b, or a square root and a regular number added or subtracted, we're going to have to multiply by what's called the conjugate. So let me define the conjugate. If we have the expression say a plus b, we call a minus b the conjugate. So basically the same exact expression with a different sign in the middle as the conjugate. And it's a handy dandy trick we use to rationalize these more complicated fractions. So we have 7 over the square root of 5 minus 2, and we want to multiply by a fraction using the conjugate. So the conjugate of square root of 5 minus 2 would be the square root of 5 plus 2. And to multiply by something equal to 1, we're going to have to do the square root of 5 plus 2 over the square root of 5 plus 2. Okay, now let's go ahead and multiply this out. So when we multiply fractions, we multiply straight across. So we'll have 7 times the square root of 5 plus 2. So when you're putting the fractions together, remember we need to keep parentheses so that we multiply by the entire numerator of the second fraction. And on the bottom, we're going to have the square root of 5 minus 2 times the square root of 5 plus 2. And I know that looks complicated, but when you have the conjugate, it actually simplifies really nicely. So let me make a new page and we'll discuss that really quickly. So whenever you have a plus b times a minus b, a number times its conjugate, it's really easy because it always just turns into a squared minus b squared. Because in order to multiply these out, we'd have to use the FOIL rule that says, okay, we multiply this first by this one, this first by the second one. Sorry about that. And then we'd multiply b by a and the second by the first. So this is FOIL. So you just make sure you get all four terms. But what would we get? We'd get a squared, the first, and then the outside terms, a times minus b, would be minus ab. The inside terms would be plus ba. And then the last term, plus b times minus b, would be minus b squared. So minus ab and plus ba cancel, and we just end up with our answer, a squared minus b squared. So in the one we're going to do, if you recall, we had something like the square root of 5 minus 2 times the square root of 5 plus 2. So what's going to end up happening is square root of 5 is like our a, and 2 is like our b. So this is just going to end up as the square root of 5 squared minus 2 squared. A squared minus b squared. So we get 5 minus 2 squared is 4. Remember, the square root and the square undo each other, so we just get 5, and then 2 squared is 4. So we just end up with actually 1. So when we go back to our fraction here, the bottom, due to the conjugate, just ends up being 1. So we just end up with 7 times the square root of 5 plus 2. And if we want to multiply that out, we distribute. We just do 7 times square root of 5, 7 times 2, and we end up with 7 square root 5 plus 14. Alright, so that one was pretty tricky, but remember the conjugate rule and remember to practice ones that look like that. The other example they have is pretty good as well. Okay, higher roots, so these are the ones we talked about. Instead of looking for something such that the number squared equals the inside, we're going to be looking for the number cubed equals the inside. And the other rules still apply. So for instance, this one, you have cube root of 9 times cube root of 6. So if you have the cube root of a times the cube root of b, this is still equal to, now instead of the square root, it's equal to the cube root of a times b. So we can start off by looking for the cube root of 9 times the cube root of 6. Well, 9 times 6 is equal to 54. So this is just the cube root of 9 times 6, which is 54. Okay, so now inside there we want to look for perfect cubes. So perfect cubes would be something like 2 times 2 times 2, which is 8. 3 times 3 times 3, which is 27. 4 times 4 times 4 is 64. So the only two cube roots we can really see that divide 54 are either going to be 8 or 27. And you can kind of see right away that that should be the cube root of 27 times 2. 27 times 2 equals 54. So we can write this as the cube root of 27 times the cube root of 2. So the cube root of 27, we just said 3 times 3 times 3 equals 27. So the first part just turns into 3, and we end up with 3 times the cube root of 2. That would be our final answer. Okay, fifth root, that's this next one. The little 5 up here tells us the fifth root. We'd be looking for a number multiplied by itself 5 times to equal the number on the inside. And remember, the first thing you want to do is if you have something like the fifth root of a over the fifth root of b, and you can combine some stuff on the inside, we should do that by making it the fifth root of a over b like this. So let's make this a big fifth root and see if we can simplify stuff on the inside. So we'd end up with 64x to the 6th over 2x. So we end up with the fifth root. 64 over 2 is just 32. And x to the 6th over x, one copy of x cancels, and we get x to the 5th power. So we can break this up into the regular numbers and the x's. So we're looking for the fifth root of 32 plus, or times the fifth root of x to the 5th. Well, the fifth root is always going to cancel with the 5th power. So the fifth root of x to the 5th is just going to be x. And how about the fifth root of 32? Well, how do we check? We just look at powers of regular numbers. So 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 one more time is 32. So because 2 to the 5th power is equal to 32, that tells us that the fifth root of 32 is just equal to the number 2. So this whole expression just ends up turning out to be 2 times x. First part is 2, second part is x. Okay, the 7c here we have the cube root of 16 times the cube root of 54. So again, we're just going to be looking to try to simplify those things in terms of cube roots. So we can start out by writing 5 times the cube root. Do you see any cube roots inside 16? Well, remember, 2 times 2 times 2 is 8, so that's a cube root. 3 times 3 times 3 is 27. We know 8 goes into 16, so let's write that as 8 times 2. And then, how about 54? 3 times 3 times 3 is 27. So we saw that we can write that as 27 times 2. So then we have the fifth root, 5 times the cube root of 8 times the cube root of 2 plus the cube root of 27 times the cube root of 2. So the cube root of 8 is equal to 2 because 2 times 2 times 2 is 8. So we have 5 times 2 times the cube root of 2. The cube root of 27 is equal to 3. So now we have terms that are like terms because we have regular numbers followed by the cube root of 2. So we have 10 times the cube root of 2 plus 3 times the cube root of 2. And we can just add those up. 10 plus 3 is 13. So we have 13 times the cube root of 2. That's our answer. Okay, so the last thing to talk about is how these exponents correspond to powers. So exponent versus radical notation. So really, we can write all of our radicals as exponents if we want, and use exponent rules and radical rules kind of interchangeably. So here's the way it works. If you would have something like 3 to the 4/5 power, what would that mean? A fractional exponent. Well, it means that the bottom number is always the root and the other one is the power. So this would, if you would use radical notation, really mean the 5th root of 3 to the 4th power. So if you have a to the n over m, basically n is the power and m is the root. So if we would have something like, say, 5 to the 1/4 power, this would mean the 4th root of 5. Say we do that 1/2 power. What does that mean? That's a good one to know, because if you have the 1/2 power, that just means the square root, where normally we don't write the 2. We just have the square root symbol, and it's understood that there's a 2 there. So square root of 9 is 3, not 2. So let's do that one again. So whenever you're converting, just remember that of the fraction, the top number is the power, and the bottom number is the root. And you can also go back the other way. So let's say convert let's say x to the 3rd power to exponent notation. So first we ask ourselves, what is the power and what is the root? So the power equals 3, the root equals 2, because it's the square root. So remember, the root goes on the bottom and the power goes on the top. So this would be equal to x to the 3/2. Power on top, root on the bottom. Okay, let's go back to the worksheet. So here we have 36 to the 1/2. We know 1/2 just means square root. So this is really equal to the square root of 36, which is equal to 6. 125 to the 2/3 power. That means we're really doing the cube root of 125 to the 2nd power. Power on top, root on the bottom. If we want to simplify, usually it's actually the same. You can do the root first and the power second if you want. So we can write this as the cube root of 125 and then do the power second. Normally this is a little bit easier to do because roots make the number smaller and powers make it bigger. So the root of 125, the cube root, 5 times 5 is 25 times 5 is 125. So we know the cube root of 125 is 5. So inside the parentheses, that's a regular 5, and we just have the squared left over. So this is equal to 25. Alright, almost done. 2 more left. Simplify this one. Okay, so things get a little bit tricky here. Let's multiply our regular numbers first. 7 times 2, and then organize our x's afterwards. X to the 1/3 times x to the 1/4. So we know that the first numbers are 14. And then what do you do with the powers here? We actually add them. So we're going to have to add 1/3 and 1/4 in the exponent. And that'll give us our final answer. So let's come back over to one of the scratch pages. And let's do that, because in order to finish that one, we're going to have to do a new page. 1/3 plus 1/4. So just a review on adding fractions. Anytime you want to add fractions, this is when we need the common denominator. So 1/3 would be, so to find a common denominator, you basically just count multiples of the bottoms till you find one in common. So 3, 6, 9, 12. Oh look, 12 is also a multiple of 4. So basically we want to make both these fractions out of 12. And then figure out what number goes on top. So what is 1/3 of 12? Well, 4 is 1/3 of 12. Because 4, 8, 12 makes 12. What is 1/4 of 12? Well, that's going to be 3. Because 3, 6, 9, 12 makes 12 in 4 pieces. So now to add these, you just add the numerators, and the denominator stays the same. It's like you're adding 4 pieces of a 12-slice pie and 3 pieces of a 12-slice pie, so we just end up with 7 pieces out of a 12-slice pie. So when we go back to the learning guide, the 1/3 plus 1/4 is just going to end up out of 7 out of 12. So we end up with 14 x to the 7 out of 12. Remember, the bottom number is the root, top is the power. So if you wanted to convert that to the other notation, it would be x to the 7th power, and you'd be taking the 12th root. Okay, so to simplify this expression, it's often easier to work in the exponent notation. So remember, 4 is the power, 6 is the root. So this is x to the 4 over 6 power, and we know we can cancel a copy of the 2 on top with a copy of 2 on the bottom. So this will just be x to the 2/3. And if you want to write that again, we can convert back to the radical notation. Root on the bottom, 3rd root of x squared. Okay, so that is kind of an introduction to the radical notation. But it's often useful to work in the exponent notation. So you saw the way we can convert back and forth between that. So remember, the bottom number is the root and the top number is the power. Okay, I hope you enjoyed this video. I'll see you again in Module 2.